Greetings of the day, dear students. In this class video, we are going to discuss about the concept of impedance and admittance. By the time we complete this video, you will understand the impedance, admittance, and for different elements, resistor, inductor, and capacitor at different frequencies, how the impedance will be, and also how to express the impedance in polar form, and we will do some problems to calculate the impedance of a given circuit, right? Yeah. Now this impedance is nothing but the ratio of phasor voltage to the phasor current. Simply we will take the ratio of phasor voltage, that is impedance Z equal to V divided by I, and this V and I represents the phasor current and phasor voltages, right? And the impedance is measured in ohm. With respect to the admittance, reciprocal of impedance is admittance, which we will express in mho or Siemens, right? Now for three different elements, three major electrical circuit elements, resistor, inductor, and capacitor, with respect to the frequency domain, voltage current relationship we will write like this. For resistor, V equal to Ri. Now what about impedance? Is simply the ratio of V and I. Therefore Z1 equal to R. If the element is only resistor, the impedance of that element is Z equal to R, right? Now what about admittance? Y equal to 1 by Z. So Y equal to 1 by R. Keep in mind if it is only resistor. Similarly, for inductor, in frequency domain, how we can write the relation between voltage and current? V equal to J omega L times I. V equal to J omega L times I. Now what about impedance? Ratio of V and I. So it will be equal to J omega L. Now admittance Y equal to 1 by Z, 1 divided by J omega L. These are important. Similarly, for capacitor, V equal to 1 by J omega C into I. Now Z equal to ratio of V and I, right? So we will get 1 divided by J omega C, and Y equal to simply J omega C. So this is how to find out the impedance and admittance of individual elements. But in a given electrical circuit, there will be the combination of the different elements. Sometimes RL element, RC element, or RLC elements, or they can be in series, parallel. Different combinations are possible, right? Then at that time, this table will be very helpful to find out the impedance. Find out the impedance. If you are asked the definition, it is the ratio of phasor voltage to phasor current. Phasor voltage to phasor current, right? Yeah. Now let me see the impedances of the elements for different frequencies. For example, what we are saying, omega equal to 2 pi f. This basic already we know. Omega equal to 2 pi f. For DC waveforms or for DC source, the frequency will be 0, right? So the impedance offered by that inductor, if you apply a DC input, if you apply a DC voltage for an inductor, for example something like this, you are having an inductor, right? And you have applied some DC, some positive, negative, 12 volts you have applied. Now just now we have discussed the impedance of this inductor, only inductor. Inductor impedance will be how much? J omega L. As and when we applied a DC whose frequency is 0, then what happens to this impedance? ZL will be 0. ZL will become 0 ohms because of the frequency of the applied voltage. Very, very important. Because of the frequency of the applied voltage, right? ZL became how much? 0 ohms. The moment it is 0 ohms, impedance is 0 ohms, it acts like a short circuit. It acts like a short circuit. Similarly, if you take capacitor, right, That means this circuit is equivalent to like this. The inductor behaves like a short circuited path and very high amount of current flows. Like this it becomes. Inductor became short circuit. If the same 12 volts is applied to a capacitor, positive, negative. But for capacitor, what is the impedance? Zc equal to 1 divided by j omega c. Now the frequency is, for this it is 0. Something by 0, the impedance became infinity. So it is almost equivalent to the capacitor behaves like a open circuit, no current flows. The moment if you apply DC here, it became open circuited. These two basics are very important with respect to the impedance when the frequency is 0. So simply to say, inductor for DC input, it behaves like a short circuit. Capacitor 1 by j omega c, omega is 0, something by 0, infinity ohms. The impedance is very high. It behaves like a open circuit. Now the same analysis for high frequencies. For example, if the frequency is very high for alternating quantity ZL equal to j omega L. Omega is infinity ohms. That means the same inductor for very high frequency input supply, it behaves like a open circuit. Very important, dear students. The impedance of inductor, if the input supply frequency is very high, it behaves like a open circuit. Simple. You just remember this j omega L. Similarly, Zc equal to 1 by omega c, 1 by j omega c. Omega is very high frequency, something infinity, something by infinity, 0 ohms. Now the same capacitor for very high frequencies, it behaves like a short circuit. It behaves like a short circuit. These four basics are very important. Clear? Right. Now let me see, we have seen the impedance is expressed as Z equal to R plus Jx. Now this R represents the real part of the impedance. Real part of impedance is the resistance. Now this X represents the imaginary part of the impedance. Imaginary part of impedance is reactance. Imaginary part of impedance is reactance. Now again, this reactance can be of due to an inductor or due to a capacitor. If it is due to inductor, it is to be called as inductive reactance. If the same reactance is due to capacitor, then it is capacitive reactance. Capacitive reactance. Clear? Yeah. Now, for example, if two elements are in series, resistor and inductor. Now what will be the impedance of the combination? Z equal to, both the elements are in series, R plus Jx. If it is inductor, the current flowing through this RL combination will be lagging the voltage. Current lags the voltage V by some angle theta. Very important. Dear students, if it is pure resistor, if this is the voltage and the current, voltage and current will be in phase. Already with respect to the inductor and capacitor basics, we have discussed this. If it is pure inductor, right, if you are having a voltage like this at an angle some 0, exactly 90 degrees, current lags the voltage I lags V by 90 degrees. If it is pure capacitor, if this is the voltage and current will be like this. Very important, dear students. Current leads the voltage by 90 degrees. This is for capacitor and this is for inductor. These basics are very important. Current leads V by How much angle? 90 degrees. Clear? But if there is a combination of R and L or R and C or LC, it depends upon the, now this angle theta equal to tan inverse of x by R, that much angle. It cannot be exactly 90 or something like that. Tan inverse of x divided by R. Clear? If it is capacitor, impedance is R minus jx, right? In capacitor context, current leads the voltage by some angle theta, by angle some theta. I leads V by angle theta. Now that angle theta equal to tan inverse of x by R. Very, very important. Now this Z, R and X all are expressed in ohms only. The units for impedance is ohm. The units for R is ohm. The units for X is also ohms. Reactance, inductive reactance or capacitive reactance. If somebody asks what are the units for inductive reactance, ohms only. For capacitive reactance, ohms only. Resistance, ohms only. Impedance, ohms. Now let me see impedance in polar form. Impedance Z can be written as some mod Z at an angle theta. Now already we know Z equal to R plus jx. Now what about its impedance mod Z? Root over R square plus x square. Root over R square plus x square. Theta equal to tan inverse of x by R. If we want real part, R equal to, just like polar to rectangle form conversion we have seen in the previous discussion, right? Now our R will be mod Z times cos theta and X will be mod Z times sin theta. What I want to say is, if somebody asks you the impedance, it is square root of R square mod Z root over R square plus X square, right? Yeah. Now let me see the different terms with respect to the concept of impedance and admittance. Impedance is, now we have written R plus jx. Admittance is reciprocal of the impedance 1 by Z, that can also be written as G plus JB. Very, very important. G plus JB. Right? Most of the students will tell Y equal to 1 by Z. But this G plus JB, most of the students, they won't remember this G plus JB. In this G plus JB, G is called the conductance. B, which is nothing but the reciprocal of reactance, is susceptance. Reciprocal of reactance is susceptance. Reciprocal of impedance is admittance. Y represents admittance. B, susceptance. G, conductance. R, resistance. X, reactance. Z, impedance. Now G, B, Y all are expressed in Siemens or mho. The units are very, very important, dear students. Right? G, B, Y. The units are Siemens or mho. Now this is where one common mistake most of the students are committing. Observe, dear students, Y equal to 1 by Z. But what is Y? G plus JB we are taking. Now Z 1 divided by R plus JX. Just simply multiply numerator and denominator with R minus JX. What we will get? R divided by R square plus X square minus G minus J times X divided by R square plus X square. This step also most of the students will do, not a problem. Now if you compare this with G plus JB, what is G here? R divided by R square plus X square. This is where most of the students will think that G is nothing but simply 1 by R. No. For example, if I give Z equals to some 6 or Z equal to 2 plus J3 is given, and you already know that the general form is Z equal to R plus JX. If I ask G, they will think that G equal to 1 by R, and they will immediately tell the answer, this is 1 by 2, no, 0.5. But this is wrong. If you are having inductive part, or if you are having reactance, if it is only Z, if I say only Z equal to 2, if there is no imaginary part, then your answer is correct. If Z equal to 2 plus J 0, then no doubt G equal to 1 by, in the place of G equal to R divided by R square plus X square. Because in the given question 2 plus J 0, as X equal to 0, what happens? R divided by R square plus 0 square, 0. Nothing but R by R square is equal to 1 by R. G equal to 1 by R. When? If X equal to 0. Very, very important, dear students. G equal to 1 by R if X equal to 0. Otherwise, if some X element is present in the problem, don't commit this mistake. You please remember this one. G equal to R divided by R square plus X square. Clear? G equal to 1 by R only if purely resistive. No other element is present, then that is okay. G equal to 1 by R if purely resistor. In the problem 2 plus J3 is given. It is not purely resistive, so you cannot take 1 by 2, 0.5, this is wrong. So G equal to R divided by R square plus X square. Now B is common, minus X divided by R square plus X square. This is how to find out the conductance and susceptance if you know the value of impedance. If you know the value of impedance, right? Now let me do some small problems. Find the impedance of the given circuit. R is given 4 ohms. Now observe, R and C are in series. Capacitor value 0.1 farad is given, right? Now what about R? As it is capacitive element, R minus Jx. But what is Xc? 1 by omega C, right? 1 by omega C. R is given 4 ohms. C equal to 0.1 microfarad. Voltage, observe, we don't know the frequency. In this formula, we don't know the frequency. Frequency, we can get it from the given voltage. V of t equal to 220 cos phi t. This is in the form of mathematical form of a sinusoidal. Mathematical form of a sinusoidal. V of t equal to Vm cos omega t. If you compare this with general form, omega is now 5. So our impedance Z equal to R minus J into 1 divided by 5 into 0.1. We will get 4 minus J2. 4 minus J2. Now what about admittance? Simple. Y equal to 1 by Z. So 1 divided by Y equal to 1 by Z. That equal to 1 divided by 4 minus J2. You just simply multiply it with 4 plus J2 and divide it with 4 plus J2. A plus B into A minus B. A square minus B square. J square minus 1 we will get. J square minus 1 we will get. That is the reason in denominator what we will get? 4 square plus 2 square we will get. That is what we have done here. If you separate the real part and imaginary part, 0.2 plus J 0.1. 0.2 plus J 0.1. Very simple. 1 divided by Z. You separate the real part and imaginary part. You separate the real part and imaginary part. Y equal to 0.2 plus J 0.1. What are the units? Observe. Mho. For this one, ohms. Clear? Yeah. Now let me do one more example. For example, if resistor, inductor and capacitor are in parallel. Otherwise, first let me see if all the three are in series. Resistor, inductor and capacitor are in series. In this problem, XL is directly given in ohms. XL equal to omega L. Very, very important. XL equal to omega L is already given in ohms. Right? XC equal to 1 by omega C. XC equal to 1 by omega C. Right? Now, Z equal to R plus J XL minus J XC. Now, R plus, take out J common. XL minus XC. What is the value of XL? Already given. no need of frequency and all those things. Directly he gave the value in ohms. So simply 31.43 XL minus XC, you will get 100 plus J31. 100 plus J31. Now you know the value of impedance in the form of, observe which sign we got at last, positive. It indicates this circuit is highly inductive in nature. For example, here you got the sign positive. How you can understand this one? Even though we are having inductor and capacitor, this circuit is highly, because of this positive sign, inductive in nature. Inductive in nature. Of course we are having capacitor also, but dominating one is inductor. For example, through somehow we got the answer Z minus J31. Then on this negative sign, seeing this negative sign, you can make a comment. It is capacitive in nature. Little bit dominating, not purely capacitive or purely inductive. That one is dominating. You looking at the sign, whether it is plus J or minus J with respect to the impedance. Clear? Yeah. Now, this rectangular form, we can express it in the polar form. Express this what Z we got. What is the value of Z? 100 plus J31. What about mod Z? Root over R square plus, because this is in the form of some R plus Jx. Mod Z equal to root over R square plus X square. Theta will be tan inverse of X by R. So 100 square plus 31 square. Now you will get 101.69. Theta tan inverse of 31 by 100. You will get 17.22. That is what we have done here. We have expressed the rectangular form in polar form. 104.69 at an angle 17.22. Clear? Yeah. Now this is the case if impedances are in series. In this entire discussion, the key point is XL equal to omega L, XC equal to 1 by omega C. On looking at the answer, if you got plus imaginary part, it indicates which one is dominating. Inductor is dominating in nature. If you got negative sign for imaginary part, it indicates capacitor is dominating, capacitive in nature, right? Yeah. Now in this example, RLC in parallel, the common mistake students are doing is, instead of writing 1 by Z, immediately they are starting it with Z. They are getting the wrong answer. In parallel combination, if you recollect the basics, if three resistors R1, R2, R3 are in parallel, looking into the circuit, what is the R equivalent value? You should start like this, 1 by R equivalent. This is important. 1 by R equivalent equal to 1 by R1 plus 1 by R2 plus 1 by R3. Instead of writing 1 by R equivalent, directly they are writing R equivalent. Because of that, the problem they are getting wrong answers. Please keep in mind, it is 1 by Z. 1 by Z. At last, you have to again convert it into Z. 1 by Z equal to same, the impedance of R, 1 by R plus 1 by JXL plus 1 divided by 1 whole divided by J omega C. Right? Now, he gave the values. Just you substitute 1 by J is there. You multiply into J by J. J square minus 1 you will get. Of course, this J omega C goes upward, right? Plus J 0.43. Just for inductor into J by J we take. That is enough. Once you got 1 by Z, now convert it into Z. This is what you will get is the 1 by Z. So Z equal to 1 divided by that one. Now again, separate the real part and imaginary part by multiplying the numerator and denominator with the negative of this one. Minus J 0.3982, like that we take. Right? So if you convert it into the separate the real part and imaginary part, what you will get is 0.0631 minus 2.511J minus 0.0631 minus 2.511J. Otherwise, you do one thing. For division sake, we have seen the calculations part. 1 means is nothing but 1 at an angle 0 only. Nothing wrong. You convert this rectangular form into polar form. Right? Now, the division of two polar numbers, the answer is very simple. If you are having R1 at an angle theta 1 whole divided by R2 at an angle theta 2, what is the answer? R1 by R2 at an angle how much? R1 by R2 at an angle theta 1 minus theta 2. R1 by R2 at an angle theta 1 minus theta 2. Once you got the polar form, then you convert it into the rectangular form. That is also okay. Right? Instead of multiplying the numerator and denominator with some other term, you express numerator in polar form and denominator also in polar form. Now you know one rule, basic. R1 at an angle theta 1 by R2 at an angle theta 2 equal to R1 by R2 at an angle theta 1 minus theta 2. Once you got the polar form, then convert it back to the rectangular form. This is also okay. Right? So these are all the basics with respect to the impedance. Right? And for example, in terms of instead of the same voltage and current division rule for resistors, how we have applied, we can apply also for the impedances. What do you mean by that? For example, two impedances Z1 and Z2 are there. If you are having two impedances Z1 and Z2 are in series, what will be the total current I flowing? Total applied voltage V divided by total impedance. What is the total impedance? Two impedances are in series, Z1 plus Z2. Just like two resistors are in series, what we are doing? R1 plus R2. In the same manner, V divided by Z1 plus Z2. If I want voltage drop only across impedance 1, V1 equal to I into Z1. But what about I? V divided by Z1 plus Z2. So indirectly, this is the voltage division rule. V1 equal to total applied voltage into same arm impedance divided by total impedance. If you recollect, it is just like V1 equal to total voltage into R1 divided by R1 plus R2, as we have seen in the resistors case. Similarly, V2 equal to total voltage into Z2, same arm impedance divided by total impedance, just like our voltage division rule for resistor. V2 equal to V into R2 divided by R1 plus R2. This is the voltage division rule we have learned. If it is current division rule, opposite resistance you will take. That's the only difference. Total current into opposite. For I1, you will take R2. That's the only difference. R2 by R1 plus R2. If I want I2, it's opposite resistance, opposite arm resistance. I into, if it is I2, I will take here R1. That's the only difference. If it is current, opposite. If it is voltage, same resistance. These two rules are very, very important to solve so many problems. That is what we have done here also. For impedances also, the current came up to here. The current is dividing into I1 and I2. Current flowing through Z1 is I1. Current flowing through Z2 is I2. Now what about I1? I1 equal to total current into opposite impedance Z2 by Z1 plus Z2. Clear? For this Z equivalent, 1 by Z equivalent equal to 1 by Z1 plus 1 by Z2. Just like if two resistors are in parallel, what you have done? R equivalent equal to R1, R2 whole divided by R1 plus R2. Similarly for impedances also, if two impedances are in parallel, Z1 and Z2 are in parallel, then your Z equivalent will be Z1 Z2 divided by Z1 plus Z2. Very, very important. Very, very important. If two impedances are in series, just like if two resistors are in series, R equivalent equal to R1 plus R2. Here also two impedances Z1 plus Z2 we will write. Clear? These are all the basics we have discussed with respect to the resistor. The same things will be applicable for this impedance. Okay. So this is what all about the concept of impedance and admittance. You should be in a position to find out the impedances and admittances for a given circuit. Clear? Keep in mind out of entire discussion, R is the resistance, X is the reactance, Z is the impedance, G is the conductance, B is the susceptance, Y is the admittance. R, X, Z will be expressed in ohm. G, B, Y are expressed in Siemens, or mho. G equal to 1 by R only if it is purely resistive, or G equal to R divided by R square plus X square. If X square equal to 0, R divided by R square plus 0, then G equal to 1 by R. Clear? Yeah. Now, one more other important point is XL equal to omega L, XC equal to 1 by omega C. Omega equal to 2 pi F. For impedance, on looking into this value itself, you can say, for example, somewhere if you got like this, Z equals to 2 plus J3, you can understand using the looking at the sign, positive sign, you can understand it as a resistor and inductor combination. For example, for the same, you got Z equals to 2 minus J3. On looking at the sign of the imaginary part, easily you can say it is for resistor and capacitor. Very, very important. Clear? Otherwise, plus J means, of course, you may have the inductive is dominant if you are having more than 3 elements, two energy storing elements, inductor and capacitor you are having in the circuit, but you got positive sign, then its meaning is inductive is dominating in nature. In the same circuit, you are also having inductor and capacitor, but you got negative sign for the impedance, its meaning is the capacitor is dominating in nature. Like that you have to understand. Clear? Yeah. Okay, students, thank you.